our guest series speaker series. I'm Sue Murray, for those of you who don't know me, the president of the Hartland Land Trust. And we'd like to introduce those of you who don't know John Raby to you. He's going to present on the geology of Hartland. John is a native of Hartland. He's very well recognized as a professional geological and hydrologist. He's done extensive work throughout his life and career. Some of the local things that he's done was he was a chairman on the Inland Wetlands Commission, president of the Hartland Historical Society, and he's been on the board of the Farmington River Watershed Association and Ancient Forests. More recently, he completed a library called the Raby Research Library, and it has collections of geology, natural sciences, mathematics, philosophy, and collections of works and letters in reference to the library. He's got mineral and artifact in the collection and an area and section for mineral identification. So without further ado, please welcome John, and he'll speak to us about the geology of Hartland. Thank you.
Recognize that guy she's talking about. With reference to the library, if anybody has old books or maps, we have a home for them. That's my pitch to you. To start, a few years ago, we built a library that's 16 and a half by 43 with another room over top of the garage where I can do mineral analysis and so on. And so that's my retirement home. And I teach a course in geology just to keep busy. What I want to do tonight is to do two things. I want to develop, if I can, some background as to what geologists look at and what geologists do, because we don't do what people think we do. They think that we go out and bang on the rocks with a hammer and bring them back and subject them to all kinds of elaborate analysis and so on, and then come up with the truth. And that's not what we do. We go out and we put together a story in the field, we gather information, and we try to fit it and challenge that story, and in the end, modify it according to what we find. So it's a constantly changing, constantly growing kind of analysis that we do. In my thesis area in Maine, my original work there was turned down because continental drift was looked at as fantasy. And today you can see what we're doing with continental drift. We have a subduction zone that goes up through that central part of Maine, and it placed some continents where people didn't think they ought to be. And so it took 8 years for that thinking to mature to the point where it was accepted in a thesis. And so geology is a growing and changing field, and it's a combination really of all of the sciences, chemistry, physics, mathematics, to tie it all together, to some degree biology as it relates to fossils, and we look at fossils by their form. Simple fossils we consider more primitive, complex fossils more recent. We think of this as a process of perfection through time or whatever. All of a sudden, the geneticists have gotten involved now, and we find ourselves more related to annelid worms than we are to monkeys or something, I don't know. But it gets really depending on what body of facts or what body of information you draw upon and regard as facts. Some of the big picture of what we look at is, and these are things that have really reshaped this in my lifetime, since the 1960s when I first got interested in this and started working on a more advanced level. One of the things that's come in is the concept of the Big Bang. The idea that at some ancient time, whatever time means, at some ancient period of time, all of a sudden all matter and energy somehow evolved, and our clocks started, mass started attracting, things started blowing apart. There was a great dynamicism that was developed in the universe. We don't know exactly when that took place, but if we use most of the different models that go back, it puts that at about 13.5, 13.6 billion years. Some people will push it back to 14 and a half. There always are people stretching the dates, and there are always people constricting the dates. That used to be an unfathomable number until you start watching the Senate. Yes. Or the Congress. And you find out that if every day you laid down a $1,000 bill, since that time has started, we would have about what the budget is. So it's a huge, huge amount of money and a huge, huge amount of time. Geologists haven't always looked at time on that kind of scale. In the 1700s, mid-1700s, coming up to the early 1800s, most of the scholars were either people from the medical field or from the clergy. And Genesis was the book of fact on which we had to base all of geology. So we had two kinds of rocks in the world: those that were before the flood and those that were after the flood. And those terms have still prevailed in a lot of the writing. They lasted up until the 1920s, 90s, where we talk about pre-diluvial sequences and stuff like that. So these concepts die hard. At that time, the age of the earth was determined by Bishop Berkeley, by reading Genesis, to be 5,000 some odd years. And so we had to cram all of the ideas that we had in geology, all of the observations that we made in the field had to be crammed into that 5,000 year period of time. In the meantime, the Asians were looking at time very differently. For them, time was a cycle and it was eternal. And so you kind of went round and round until you got it right, which is what we end up doing now, never get it right. But anyway, they went round and round in their system, and so huge, huge amounts of time didn't scare them. And they set, through philosophical reasoning, the age of the Earth, the Earth itself, not the Big Bang in the universe, the Earth, at about 4.6, 4.5, 4.6 billion years, somewhere in there. With our best technology today, we vary from those philosophical numbers by less than 10%. It's absolutely incredible what some of these people came up with. And not only did the people in India do this, people in China did the same thing, and it took another almost 200 years for people to read those documents, and ended up with exactly the same dates. Both of these cultures reasoning to that same period of time. So I put in a little something about that in this introduction. Now, at sometime in the late 1700s, 1796, 1795, 1796, Laplace was looking at energy in gases. And he said that if you take a whirling amount of gas, it will automatically condense on itself. As soon as two particles, gravity will attract a third, so on and so forth. You get this cascading kind of collapse. This is the condensation theory for the solar system. Actually, he talked about the whole universe in the first part, the first paper, then that was tightened down on the Earth, on the Earth itself. The idea is that this great whirling mass of gases somehow develops a knob, a clot in it. And that clot gets in the center and stuff falls into that with tremendous speed. So it takes the background temperature of the universe and it crams it into a tiny, tiny place. So all the energy that used to be spread out all over the place, and the universe is mostly space, sort of, and it all comes cramming in, and you get a huge, huge amount of energy given off, and the gases that are there, the mass that's there, starts to glow, and ultimately it actually comes apart into some particles and so on and so forth. And we have a center to this. That center attracts mass until it cleans out the area near it, and then these other clots take over, and they orbit that first one, because after all, this was a whirling mass of gases. And when you bring those gas particles together, they don't forget where they were. They keep going in the same direction they were going originally. And without very many exceptions, there are a few, there's one exception, the planets circulate around the sun in the same direction. And the timing is such that we can work the masses back and get them sort of out of the whirling gases that surround the sun. So that idea, which was put forth in the late 1700s with this awakening of science, and all of a sudden people making observations, and what you saw with your eyes took precedent over what you were taught by the dogma. We developed geology at that time as we know it today. It came out of looking at rocks, looking at where certain rocks are at an angle and they've been beveled off and other rocks are on top of them. The classic example is Point Siccar, where one of the early geologists first noticed all this missing time, and he said, you know, you can't put these rocks up on end and erode them away and put new rocks on top of them without spending a lot more than 5,000 years, because how do you do that? How do you get rid of all those sediments? Where do they go? And so all of a sudden we start stretching time, and we start coming up with estimates for the age of the Earth, that is the crust of the Earth, as being 1.5 million, 2 million years old, numbers like that. That seemed like an awful lot to these guys. And so they started pushing this 5,000 year date back to several million. As time went on, a principle developed called the principle of uniformitarianism. The idea is that the processes that operate on the Earth today, that you can discover through careful observation, operated on the Earth in the past in essentially the same way that they're operating now. That is, water flowed downhill, sediments were dragged off the ground, water acted as a solvent for salts, etc., etc., etc. That idea, the idea of uniformitarianism, insisted on even larger amounts of time. And we start pushing the time back and back and back. And all of a sudden, we have room in that time scale for very small variations to develop into new species and so on and so forth. So we accommodate the basic concepts of an evolution of form, or a changing of form. And of course, Darwin comes along, and between Darwin and other members of his family, they put together this idea that we see today as physical evolution of things. Now, physical evolution, some people really balk at this idea because they feel that there's constant creationism going on, or that there was once creation and everything was set in motion and it moved through time. These are largely different perspectives of the same phenomena. It depends on the philosophy, the beliefs that you have, how you are going to treat those so-called facts. The fact is, rocks that are on the bottom of the pile have fossils that are more primitive than the rocks on top of the pile. It's as simple as that. Now, whether there's divine hand in that, shaping that, or what, becomes a philosophical argument. The fact is, the deeper you go in those rocks, the more primitive the fossils. One of the arguments that was made against this idea of creationism coming along through time is that animals became extinct. And if you have an infallible hand, then why did animals become extinct? So as we come through the early 1800s, there are people finding these alligator fossils, they call them, and so on, particularly Lyme Regis on the south part of Great Britain. And they would get these skeletons. Some of these skeletons were 35, 40 feet long, great big vertebrae on them, and so on. And they said, well, these are alligators. This is some kind of alligator. One of them, they said, was descended from a hippopotamus. They took the tooth off it. They sent the tooth over to France, to Cuvier. He picked it up and he says, it's a hippopotamus tooth. Here, take it back. He didn't want to mess with it. He said, I can't, it's just, doesn't have any significance. Well, it later turned out that this was the tooth of an ichthyosaur. And so all of a sudden, all these massive animals that were discovered in the fossil record, they were too obvious to be the results of lightning strikes, which is what some people said they were. And so we had born paleontology. And one of the reasons that we today use fossils so effectively in timing and aging rocks is because of the work by one Buckland, who was a clergyman at the time, and he collected, there are millions of stories about this guy, and he collected fossils in his little bag. Well, he had this bag he used to carry around his neck, hung down to the ground, and he had a horse, and he'd mount that horse and ride around the countryside. The horse was so used to stopping at every quarry that some guy borrowed his horse one time, and the horse heard somebody chipping rock, and he stopped, wouldn't go any farther. So the guy had to get off, bang on the ground a little bit, and then go back, get on the horse, and away they went. But that horse was so used to stopping that it just wouldn't go on until you checked out the rocks. And Buckland was very important because he rose to extreme prominence in England and in the Royal Society. And this was a time when women who actually were carrying much of the load in the science just were not revered and were not allowed to be members or even attend the formal meetings. So these women were preparing the documents. They were putting in the drawings. They were doing often the field work. Mary Anning did the field work. She actually collected the fossils. And she was prohibited from giving these papers or anything. Buckland did all of that. And as a tribute to her, she died of breast cancer. And in her late years, he got the Royal Society to read one of the papers and dedicate it to her, which was a big breakthrough at that time. Himself jumped in a coach to go somewhere one day, and he sees this really good-looking woman sitting across from him. Well, he can't resist this, so he's eyeing her all over. And he looks in her hands, and she's got the latest copy of Cuvier's book on fossils and comparative anatomy out of France. So, hey, not only good-looking, but great cells. So he started talking to her, struck up a conversation with her, and ended up marrying her. And she did much of Buckland's actual work. So at that time, geology was getting its foothold to be kind of what it is today. I put in here a little something about geologic time and this story about how long geologic time goes and how we can look at it and think about it. And there's a little thing in here about every year a bird lands on a rock off the coast of Norway and sharpens its beak after eating some of the seaweed that's on the rock. And over time it wears the rock away, and that whole period of time is nothing but a snap of the fingers in geologic time. And that was the thinking that was coming out of during that period. The habitability of the Earth is a very big problem. And we have to address the habitability because that's the oldest rock that we can date using fossils. If there are no fossils, if we pre-fossil, that type of life, we can't use anything to date the rocks, except maybe some radioactive, radiometric dates or something like that. Now, there's a strange thing that happened, and this upset geologists a great deal. What happened is they started looking at fossils, and they found lots of fossils in New York State, for example. Everybody was out in New York State collecting fossils. In England, they're all out there pounding on the rocks, gathering fossils. They're similar to some rocks in Scotland. They send some people down to Italy. They find some shells down in Italy that look the same. They're all worked up. This is the beginning of life. So they gather all these fossils up, and they find out that most of them look a lot alike. But in each place, there are some that don't fit. And one of the great geologists, Lyell, came to this country, and he traveled around here. A fantastic travelogue about going to Niagara Falls and figuring out how long it took the falls to retreat, how his logic for the rate of retreat, which is the same logic we use today. It's exactly the same number we get today. He worked that out. So these guys are roaming around doing this kind of stuff. They're going down through the Avignon region in France, looking at basalt, like you see if you go over near Roncaris, okay? And they say, these things don't look like sedimentary rocks. I know where there are volcanoes that look like that, where the rocks look like that. And what was happening was they were going down to Italy, and on their way to Italy, of course, they passed some active volcanoes. And so they said, hey, it's just like the stuff that's coming out of the ground now, and so on. So that region became a kind of a testing ground for whether basalt was precipitated from the Great Flood or whether it was an emanation from a deep-seated source, whether it was something that came from depths within the earth. And so these abundant fossils started to be the working tools of geology. If we look at some of the works of Stephen Jay Gould, you can have various mixed opinions about him. My opinion of him changes like each time you read one of his essays. But he wrote, one of his volumes is called Mountain of Clams and Diet of Worms. And the Diet of Worms is a play on the document. And Mountain of Clams is the pelecypods and brachiopods that were found in Italy on two sides of a valley, and therefore the rocks on each side were correlated and thought to have once gone through the valley and connected. And therefore the river had opened up that valley. Now, again, you see we're hammering at that amount of time. We don't know for sure what happened that got life going. There are lots of theories. For a long while, in the 1950s, actually a little earlier, but through the 50s and up to the 70s when I was involved in that sort of stuff, people were making amino acids. That was considered the trick. That was the alchemy of the time. And you would mix together some certain gases and water vapor, some carbon dioxide, some nitrous oxide, maybe some sulfur, some other odds and ends of things, and you'd heat them up to a moderate temperature and put electrical shocks through it. And what you would get is a fog on the inside of the glass. When you poured it out and analyzed it, you would get certain amino acids. Now I put a little summary in here, Miller's work and so on, that goes through that process. But that was the chemical stuff that we did. You remember a few years ago, there was a newspaper headline about life on Mars, that a meteor had hit Mars and exploded a chunk of the Martian surface off, and it had landed in the hands of NASA. They concluded that those little bumps on there were actually a particular strain of bacteria called Cyanobacter. And this was a big deal because one of the theories for the origin of life is that life in some form or another scattered throughout the universe, and it just falls on things from time to time, like casting seed on soil. And where it's fertile and you have the Goldilocks planet, you get, everything is lined up and stuff takes off, and lo and behold, you end up with people, or hippopotamuses or something. But life takes hold and increases in complexity. One of the great mysteries which is being argued today is, why does life seem to look more complex all the time? Why is it that we keep adding things and combining things? And that's a philosophical question. That's something that has to do with the way that we observe life forms and so on. I put in the handout a picture of geologic time since the beginning of the fossil record. And it's kind of mushy back toward the beginning, but by the time we get to about 3.2 billion years ago, we got some darn nice looking fossils. We got some stuff that you can't help but think was alive, namely some little sponges. They're sponges that make their cells out of glass, the heliosponges, and they are pretty certain to be early fossils. These things get really going by the time of the gunflint formation, but it's hard to find these fossils. There aren't many of them. One of the important things that happened geologically is people were out in British Columbia looking at the black shales, chipping away at them. And if you go there early in the morning, the black shales encourage the condensation of water on them in a kind of a fog. And if you turn them in the light, the imprints of living shapes appear on those surfaces. There's a thin layer which you can coax information from with electron microscopy, but with a naked eye or to go to scrape it, you can't get anything off there. And so it was thought that this was, in the words of some of the earlier investigators, the slimy remains of an ancient life form, an ancient animal. So people have been digging these things up, and they turn out to be jellyfish of certain types. An ancient, fairly ancient form, but when you look at a jellyfish is actually fairly complex. And a lot of jellyfish have developed very elaborate systems to synthesize and use poisons or digesting agents and so on and so forth. So they've certainly been around a while, and you can find these fossils in the Burgess Shale. And Stephen Jay Gould wrote his famous book, Wonderful Life, great read about the Burgess Shale and the implications of it. Now, only a short time after that, by a short time I'm talking about a few tens of millions of years after that, all of a sudden there were 12,000 species of shelly fauna in the oceans. 12,000 species. Where the devil those things come from? Well, they must have been in there in some form or another, but didn't have shells, so they couldn't make fossils very well. So our abundance must be prejudiced by the fact that when they got hard parts and could make fossils, we found lots of them. Before that, they were hard to find. So people started looking, how come they could make fossils? How come they could make hard parts? And it turns out, if you mess around with the data and look at inclusions in quartz and things like that, you can come up with the composition of the atmosphere. And what was happening was we had not enough CO2 in the atmosphere. So the forces that were available to an organism, the life forces, the metabolic differentials that could be created to pull that CO2 out of the water, which was in equilibrium with the atmosphere, just couldn't make a shell. In fact, the early shells don't have carbonate shells on them. They're made of chitin, same stuff as your fingernail. Okay? So we know the organisms were making shells, but they weren't yet able to pull this material out of water effectively. It had to wait for the CO2 levels to come up. Then, within a very short time, that happened right at the bottom of this in the Cambrian time, right here, 550 million years ago. From here, we have only a few fossils. Here, we have tons of fossils. Few here, lots here. This little thing is put together by Pantera, shows the position of the continental cores and all that kind of stuff, but that's not something we got to worry about tonight. By the time we're in the Ordovician, we're producing whole 200, 500, even 1,000-foot thick layers of carbonates. They're precipitated water. It's easy to make a shell. We can even work out, by the isotope analysis of that stuff, we can work out what the temperature of the water was, whether they were in a temperate region or not, by the differences in the oxygen 18, oxygen 16 ratios, and so on, and get very, very accurate dates. Well, all that was kind of exciting. People got really worked up in that. So then they said, well, let's look at glacial sediments. This is going to bear on us in a few minutes. Let's look at glacial sediments and see what we find. So they go out in the ocean, and we have, until then, 4 great ice ages. Okay? And the last one, of course, is the one that paints the top coat on everything. So we have a first one that comes in, a second one overrides it, a third one doesn't come quite so far, and a fourth one covers everything. So you only get to see the top coat of paint on the surface. If you go out to the ocean and you drop a probe down there, you can pull up the sediments that were being accumulated during that time. So you pull those sediments up and you start looking at the oxygen 18, oxygen 16 ratios in those sediments, and what you find is that you can work out the temperatures and figure out when it was warm, when it was cool. And boy, did that screw everything up. Because all of a sudden we didn't have 4 great ice ages. We have 4 advances of ice on the land. But they ain't related very closely to these fluctuations. It takes moisture, it takes time, it takes a warm air to carry the moisture to make the glacier. Also, glaciers tend to form when you get enough ice so it makes it through the summer and reflects light. The difference between an unglaciated surface or a surface without ice and a surface that's got dirty ice on it is tremendous in terms of the heat absorption. You go right out today and you look out here at the roads thawed off. You look at these muddy, ugly looking banks. They got holes in them where the warmth has melted that stuff out or has actually evaporated water directly from the ice by ablation. So you can see this effect around you everywhere. And so that was a huge breakthrough. All right, so that I don't go on to midnight here, let's turn to Hartland and see what we get to see here. Well, our rocks are in Hartland are mainly rocks that are churned up ancient rocks. They all have ages down in this range, down in here. They're Paleozoic in age. If they had fossils still left in them, we would find Paleozoic fossils. Paleozoic, you can turn to, there's a little chart in there that has all these names in there and times associated with them and so on. Looks like that. Okay. And if you look at the rocks that we have here, all the rocks of Hartland are rocks that were either deposited or mauled over by geological processes right here in the eastern geosyncline, right in this part of this sheet, this side of the sheet. All right? And there are 3 events that we like to distinguish in these rocks. The first of these events is called the Taconian event, named for the tectonic mountains. What happened in this event? Well, if you believe in plate tectonics, which nowadays you have to or you can't get a job anywhere, so the plate is going down underneath the edge of the continent, and as it starts to go down there, it slams energy up against the continent, and it blows these areas back against the continental mass. If you go to the way back of this thing I made here. Maybe I didn't put it in. I thought I did. Here it is. Here's a picture of what one of those subducting plates or collision of continents looks like. And part of it is sliding down under the continent. It has to push against something. So the other side of the continent, the Pacific half of the continent, is anchored. It isn't going anywhere. So as the land is moving in the Atlantic, it's pushed over and slides down under the continent, and it shoves the mountains, the tectonic mountains, in a great slice up into the area where we see them today. In the west, much later, when the western geosyncline is deforming, we find Chief Mountain. Chief Mountain is an overthrust with the carvings on it and everything. If you go to the bottom of that, there's a fault there, and that material that's in the mountain belongs 100 miles away or something, some great distance away, been shoved up on the land. So early in the deformation of land, there are these events which slide the material great distances up onto the land. There's evidence of that in these rocks. Complicated, hard to get to, but there's evidence of it. If we look at the next stage, which is the Akkadian stage, also in Northern Europe called the Caledonian stage, the rocks that are typical of that time are the great granite bodies. And similarly, you can go to that sheet that's in the back that has the sections of what's happening, and you'll see there are little granites shown in the diagram. They look like little mushrooms coming up. They don't look very big. But those things are huge. That's the green, rather the white mountains, the great plutons of the central part of Maine, over into New Hampshire, and to some degree underlying the rocks in Vermont. And then finally, this whole thing gets really cooking, and in the Permian time, it's a little bit misrepresented here because of some peculiarities of that chart. But at any rate, in that time, the Hercynian in Europe, the Appalachian in the United States, we have an event that builds up, and boom, everything gets folded. At that time, the sediments that were folded were coarser from the east. Gravels on the eastern edge of those sediments, sands in the middle, limestones and shales toward the continent of today. Those things were coming from some other place out in the ocean. Well, there was no ocean there. The place they were coming from was North Africa. Africa was backed in against the continent at that time. There was a highland that was to the northeast in Africa today, and that was shedding those sediments. After that happened, that energy that poured up out of there allowed those rocks to congeal and harden. And then the upwelling of energy in the Atlantic was sufficient, that plate having been glued to the continent, to push it and make the west coast break. And so the whole process started over again on the west coast with subduction under where is now the Rockies. All right? Meantime, over on the east coast, where it's all glued to the continent, energy keeps piling up, gases coming off, water vapor, so on. We like uncorking a champagne bottle, the degassing of these basalts goes on, and it pushes up and makes the mid-Atlantic ridge and spreads the Atlantic. And the Atlantic, at the top of the Permian, looked then just like the great Rift Valley of Africa looks today, where the fault starts at Madagascar in the Madagascar deeps and runs up next to Kilimanjaro, crosses over onto the upper part of the Red Sea, and goes up the Jordan Valley and is lost against the great mountains, the Hers Mountains or whatever, that are in the same chain as the Himalayas. So the process is always the same in an orogeny, in a mountain building event. Oros mountain building, orogeny, mountain building event. It's always the same. Starts out with thrusting, sort of dry thrusting, then you have emplacement of the great granite bodies, diorites, loaded with gold. I mean, that's good stuff. They come in and like the Sierra Nevada, okay? And then the last event is a folding event that tends to seal things up, and then the area cools and starts to collapse. And as it collapses, there's still a few basalts that ooze out. In the east, it's the Palisades, it's the Triassic Valley of Connecticut, places like that. So the process then, down in here, we have all that thrusting going on. Up in here, we have, actually right here in the Devonian, we have the great plutons coming in. And then we have the mountains built here. And then right here we have the collapses that are the Triassic Valley of Connecticut. And this shows where the sources of sediments are. On this map's another interesting thing. There are these red dots. And these red dots represent the size of a meteorite that would have to hit the Earth to produce the kinds of changes that we see. So they're implied by the relationships here. And when you go out in the field, you can't find them all sometimes. But they're theoretically there. And in recent years, we have found more and more and more of these. So the idea that this timing and this movement of the continents and all is related somehow to bombardment is, it's gaining, or it comes up from time to time as a notion. And that chart kind of summarizes it. It's a chart by Pantera, and it shows the various animals at each geologic period, so on and so forth. Now, all three of those events make up this complex of rocks right here. That stuff. There's a red line in here. The rocks on top of that red line came up as a great fold, and they flopped over on the landscape. Those rocks are upside down. They got squeezed up, squeezed up, squeezed up, like filling a balloon with water, and the balloon gets up in the air and flops over. That's what those are. These rocks were deep in the Appalachians. This doesn't happen on the surface. We're talking about rocks that were approximately, they had about 6 kilobars of pressure on them. A bar is 15 pounds per square inch, 1 atmosphere. All right? So you're talking about something with thousands of pounds of pressure on them at that time, and some considerable heat. We can actually work out those temperatures very, very accurately. We can get them within tens of degrees, 100 degrees, less than 100 degrees, tens of degrees, and we can get the pressures very, very accurately. I put out some examples over there that you can look at. But one of the things we get is a triple point, a place where 3 minerals that all look very different but have exactly the same chemical composition, and they come out in equilibrium. Each one is eating the other one and making new ones all the time in equilibrium. This is called triple points, just like triple point of steam, water, and ice. And it sets those conditions very accurately. If you can find those 3 minerals preserved in a rock, and it has to be a kind of special case because you got to get rid of the water. If you don't get rid of the water, when you start to bring the rock to the surface, the darn thing goes bad. So you got to get rid of the water. It's like making a snowball. If you make a snowball, you don't squeeze it enough, it didn't stay together. Same kind of idea. So bring that back up to the surface, and you get that triple point. And there's one, not in Hartland, although we got a lot of nice kyanite here. There's a sample right over there. But if you go to the top of Soapstone Hill in Torrington, that's where the triple point is for the metamorphism that went on here. And you can find sylvanite, kyanite, and andalusite all in equilibrium. I brought over one of the rocks over there from that location. So we get that, tells us a lot about this area. This is sometimes called the Eastern Upland or the Eastern Crystalline Highland. These are the rocks that are all churned up and cranked up and so on. The central part of the map, 2 big faults, it's dropped down. It used to be way out here. In fact, faults parallel to these go right down and make the fault that goes down the reservoir. Goes right down and goes right through the fountain. The fountain that used to run at the south end of the reservoir is right on the fault. you could, years ago, when you could go down there, you could stand, look across the fountain, and look south, and you could actually see where the rocks lay together on that fault. So there's one there. If you then go farther, you go over to East River Road. East River Road runs along the next fault. And you can go over there and see the location of the gravels and so on and so forth, and figure out the position of that fault. So you have one here, no red rocks. You have one here, no red rocks. And you have one a little farther over, and man, red rocks everywhere. Actually, if you go south on the fault that doesn't have any red rock up in Hartland area, and you get down to Cherry Brook, at Cherry Brook, there's a little area of red rock, and that stuff is really cooked up. A driller by the name of the Dominicus took a course from me years ago. Came in one night with a bag of these things and dumped them across the desk, and they were all boulders that he'd gotten out of a well, and they ranged from the size of golf balls up to about the size of tennis balls, and they were all heat cracked from the movement along that fault. And he'd been up there drilling a well just, if you go up past the town office buildings now and keep following the road jogs over to the right, and there's a big sign up there that says, "Caution, geese crossing," because the people live in that house have some geese that go across the road to the water. You go about 100 feet past that, walk out to the stream, and there it is, red beds. A chunk, a little remnant of that Triassic valley that's still left there. But we have a lot of it out in the main valley. You can see it's cut by hundreds and hundreds and hundreds of faults in it. And some of these are deep faults and some are not as deep. If we then move over to the far east, these rocks, you look at those rocks and it's more scrambled. You know, the printer's ink is kind of all over the place there. Over here, it seems to have a little bit more order to it. And this is a rooted area. This is an area where that big structure came from that went over and laid on top of it. These rocks here are in their normal place, but when they got lifted up and flopped down here, they're above Logan's line. They're above that red line. So that's the place that the balloon was being blown up and plopped over there. And that's why it's more orderly, because that's the root of one of these things. And if you look at those drawings in the back of the handout, you'll see that that's exactly what you would expect, because you're in the middle of that, like the fourth drawing there of the continental boundary. This thing is building up, and it's going to flop over and be left. It's going to leave windows, or fensters, as they like to call them, that allow you to look down on the underlying rocks. Okay, so that's pretty much the bedrock geology that we have. We have no fossils. They've all been cooked up. This rock has been mauled and mutilated, and at very high temperatures and pressures. At those temperatures and pressures, the fossils gas off, so we don't have fossils left. We do have, in a few places, some rotate, what they call rock cleavage, terrible term, but we have some evidence that as to how these things have moved. And I brought with me a couple of samples from the Hartland Formation that show an initial compressive movement, just like you took a bunch of paper and crushed it in a wastebasket, sawed through it. You would have foliation. There'd be a tendency for particles to line up. And then if you squished it like that, you'd have a single shearing event. If you squished it like that and then went like that, you'd have two at right angles. If you went and then went at an angle, you'd have two where the second one is not at right angles. So I brought samples of all of those along here so you can take a look at those on the side table over there, and there's an explanation on it. So I will go very, very quickly through the glaciation here and take my slap at the DEP. Not my favorite people when it comes to geology, but they do. For math designed by a committee, that's not too bad. You know, they always say you never should watch laws being made or sausage. Bismarck said never watch. Never wanted to see sausage or laws being made. Well, there's a map that's made that way. I'm sure they sat down and got all kinds of consensus. You can't read the blinking thing. Here's the stratigraphy, or the order of the stack of rocks or sediments. You tell me you're going to figure that out. But it actually is a gold mine of information. This thing has tons and tons of information, done very carefully, and now with the digitization that we have and the denser matrix that's used, we can get an awful lot of information out of these. And you see even on this, there's some kinds of sediments that are still mimicking that central valley. In fact, one of the curious things about Connecticut is we don't have any decent east-west roads. We got Route 44, that's about it. And it's maybe, sort of, but we don't have any east-west roads. All kinds of north-south roads. And our attitudes are even built that way. If you talk to people, they talk about running down to Waterbury. You know, I mean, I'd run from Waterbury. Make a run down to Waterbury, all right? Here we talk about making a run into Hartford. We're going right where the water goes. We're going downhill, down valley. When the glacier came over this area, it stroked the land in a north-south way. And that made it hard to travel across the corrugations and easier to travel with them. And since civilization is driven by water, whether you're going to drink it or use it to power things, you tend to find civilization spreading along the major rivers, which again tend to be north-south because of the corrugation. If you go south of here, where there was a great flat area when the Susquehanna River was formed, and it came meandering down across that area, and then that eroded down, 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 down into a corrugated landscape, there what you find is a resistance to east-west travel because of the corrugated landscape, unless you're going where the river is. And then you can get through. So if you look at the Susquehanna Water Gap, it is wall-to-wall railroad tracks. All right? It also is why you get good Scotch whiskey down there, because the people in the hinterland couldn't get their crops out in a normal way, so they went into the added value business, and they spruced them up so they were more portable and worth more per trip. Okay, well that's the geological or the glacial map. This is one of my favorite maps of all. You can still see that structure. This map was constructed almost solely by Richard Flint. Probably, in my opinion, at least the greatest of the Pleistocene quaternary geologists. He was at Yale. Tremendously insightful person. And if you take this map, you look at it carefully, you can see all these little places where there were dams that dammed up something for a while, and then they washed out, and then it went in back of another dam, and so on. So you have all these still stands and all. And these are the sources of eskers, which are long, sinuous ridges, or in some cases cames, but economic deposits of sand and gravel. I didn't bring it with me because it was raining. I have an original textbook or a book published by the state. I put over here one of Percival's early books, but the other one is a lot bigger. And it has a photograph in it taken from Sunset Road, looking south along all those gravel banks, which at that time were open. Their animals grazed on that. It's all open meadow. And you can see this esker going down, and ends up in back of the old Gower place, in back of Wade Raby's house, and finally in back of what was the Sturman property. It ends up down in the state forest down there where it peters out. If you go down and walk that, right next to that's a swamp. You go through the swamp, and then you step up onto the gravels. That's because they were laid down at the mouth of streams that were encased in ice. So you got the ice with a hole in it, and that stream goes through there and it lays down gravel because it's all encased and it's flowing fast. All right, it lays down that gravel, and then it melts, and so the area where the ice protected the land, kept it from having gravel, you have a slight depression. And all the glop and the vegetation and everything that's associated with the glacier and with the glacial lake that forms when the land is being squeezed down and depressed by the weight of the glacial ice, all of that is related to that wetland. If you go to the Council Caves, you'll see you go through an area where there's gravel, and then you go through these wetlands right in front of the council caves. And these wetlands, they're tremendously valuable, of course, as habitat, because they're next to these gravels. You get a lot of diversity in the upland versus the wetland areas. You get a tremendous edge effect and so on, but you also get one heck of a lot of methane. And methane is about 70 times more effective in causing global warming or atmospheric warming than is CO2. In fact, recent studies have shown that the droughts in the tropics, in the rainforest I should say, are releasing more methane to produce warming effects than all of the fossil fuels consumed by mankind. So tremendous warming coming from that area. In the past, if you go to the 018, 016 numbers, big deal to do them in here and there, you come up with the fact that the Earth has been warmer than it is right now, about 70% of its history. So we're not at the warmest time. That isn't to say that things are going to be so nice when it gets warm. But it does kind of say that we are pretty arrogant to think that we can do what nature has done in the past a lot more effectively than we have. And if we stop all of our use, not that we shouldn't be careful, but if we stop all of our use of fossil fuels and whatnot, it ain't going to stop this. It may set it back a little bit. It may shift it over to some other gas, whatever. And like I say, you know, you got to be foolish if you're wasting resources. But by the same token, you can't expect more than you're likely to get out of your activity. So that's one of the lessons that comes out of looking at glaciers. So on. Also, glaciers in the 1960s, when I was an undergraduate, way back then, I used to ride a dinosaur. School. But back then, the idea was we were coming into an ice age. Someone had a bunch of precipitation data from Scandinavia. And they said, holy smoke, we're going to be in an ice age. There's a glacier that surges 150 feet a year over in Switzerland. You know, now we're worried that it's surging because it's getting warm. An arete, in the sense of an excavated structure that under the ice was changing so that we were getting a different ice field and therefore a different ice flow. So you got to tally all this up, and that's what this guy's thesis was. That's what he was doing, is he had made computer models to tally up, to make some kind of sum total, try to get an idea of the thickness. We had some remote sensing data that we could use, and we got an idea of the thickness of these things and the densities of the ice, and we had seasonal temperatures taken from satellites and from U-2 overflights, and we were able to work out some kind of a model. And it was very interesting because when he did the presentation at the end, one of the students, students could always ask questions to presenters, so the guy gives a presentation. One of the students says, so what was your conclusion? He says, conclusion? There is none. So that was the result of that study. I mean, there's a lot of data, but not much conclusion. So anyhow, the glaciers affect our lifestyles a lot. It affects us here in Hartland particularly because we do have a lot of glacial fabric on our land, imposed on our land, and to a large extent it is shaped by the imperfections, the corrugations, if you will, in the crystalline rocks. This area has been rendered flat, absolutely dead nuts flat, at least 3 times. Some think 5. If you want to see a flat area, you go over to the firehouse in, not Riverton, isn't that all? Pleasant Valley. Firehouse on the side hill there. All the hills, same height. You go to the top of the hills, and they got swamps on them. They don't drain. You go over to the Seville Dam. Look north from the Seville Dam. Flat areas, flat area, Swamps on top, West Hartland, full of swamps on the tops of the hills, shallow to bedrock, lots of swamps. All right? The old Day property, for example. We did a hydraulic study in there, and, you know, I don't know how they plowed it. A lot of places were very shallow. Some places there were actually some darn nice soils, but in general, it's a typical hilltop in a glaciated area. You've got to pick the area where you're going to do your work very, very carefully. And land is precious. You have to go in and do your testing for whatever you're going to do, whether you're going to grow potatoes or put a septic system. And you've got to look at that very carefully and then set that aside to do that. Because if you waste that on something else, that folly will cost you. You won't be able to do what you want on the land. So glaciation has affected New Englanders. Stanley Ransom used to say that glaciation was the reason for the shape of a sheep's nose, because they had to eat the grass between the rocks. And maybe that's sort of the case, that there's an old thing about the land was so rocky they had to sharpen the sheep's nose. But the glaciers had a big effect on us here, and that's the last coating on the land. So that's pretty much a summary of what went on. In your handout, I have the positions of the continents, if you care. I have the positions of the continents with the geosynclines between them, taken from the studies done in the 1960s and early 1970s that reshaped the thinking of geology at that time. I took some of the classic ones of those and just made a copy of them, attached them at the end as to kind of where the information comes from. But we can't forget that though a lot of this looks technical, and to some degree is technical, I mean, you do magnetic pole studies, man. But the bottom line is, it's got to fit the story, or you got to modify the story if you believe in the data. And so we constantly build a more and more complex story and understanding of the land. This is Klaus Pankowski, who was a geologist from the University of Hawaii, used to come to New England to do geology. And he said that if you can do geology in New England, you can do geology anywhere in the world. And he had been all over the world. He'd done a lot of geology in Russia and so on. And he said these rocks are the most challenging rocks in the world to untangle and understand. And I suspect that that's true. We really have a worm's eye view of a mountain range. The top is eroded away. John Rogers at Yale, when the Intercollegiate Geological Conference was held there, he wrote a paper for that. And the last line in that paper is, "So welcome to Connecticut, the worm's eye view of the Appalachian Mountains." And so that's kind of what it is, and that's the view we have. Our rocks are very highly metamorphosed. They represent a great depth of erosion, perhaps something like 20 to 30,000 feet of erosion material from Olders. So this is the ultra worm's eye view here, and yet it's an upland crystalline rocks with swamps on top. All right, so that's pretty much it. If you want to look at the side table over here, I brought along all kinds of odds and ends of things. They're heavy, so please look at them or I'll be insulted having carried them. And I'm mad at you, but anyway.
Does anybody have any questions? Or?
There's one thing over there worth looking at is I have some fossils from when the continents were together and the proof that they were together. They actually are from New South Wales and Australia, but that is the fossil that puts Africa, South America, and Australia together. You had a question?
I do. I'm actually from Granville, but I'm not so far off. I don't think.
You're in exactly the same thing we have.
Yeah. And back when we had earthquake in the late 90s, I couldn't find anybody to get any information from. You know, there was like 2 newspaper articles. I called some of the colleges. I couldn't find anything about it, but I did hear there was a fault line in your Granville. Is it part of one of those fault lines?
There are fault lines. They're really what we should call hinge lines. What's going on is the Earth has been squeezed down by glaciation. As the glacier piled on the Earth, like people climbing on a dock, it pushes it down. And then the glacier goes away. And so from time to time, that land recovers, it uplifts. And it's not an altogether smooth process. If you go up to Lake Champlain, one whole side of Lake Champlain is now hinged and recovering. And it recovers about 2.5 feet in a quake. We have some friends there, and he was looking out over the lake, and he said all of a sudden the whole lake started shimmering, and then the house started shaking, and he thought the dog had jumped on his bed because he could hear it, but he couldn't really feel it. Well, the house is like a fortress. So, but we've had several earthquakes here. And one morning, I was laying in bed at the corner house up here, and I felt this trembling, all right? And hadn't been out the night before, so I knew it was some natural thing. I jumped out of bed. I said, that's an earthquake. I want to see where it's coming from. And I looked out at the power lines. And the power lines that went up Walnut Hill were making long loops, and the other power lines that came down 179 were making small loops. And it turned out that that earthquake was the result of movement along one of the hinge lines where the western side sprung up relative to the St. Lawrence Valley, of all places. But we have these all through this area. And if you look at how significant these are, when soils or when gravel is laid down from the glacier, it's laid down essentially flat and low gradient. Okay? And then it uplifts. Now the darn stuff is slanted opposite the direction it was laid down. And this goes on all over the place. These are called still stands in between this and tilting when it goes on. Dr. Luigi, Swiss, who came to this country, was not very respected. He was ridiculed immensely. I went to Clark University. One of the reasons I went there was to study with Luigi. He died the summer that I was there. But I managed to get a hold of his book, which was edited by Professor Reese down at Yale. And it goes through all of his studies. I have a few of his papers and stuff. When he died, his wife came in and locked his office because people were stealing his data. And so she managed to get all that data into trunks, got it out of there, got it down to Yale. Reese put a lot of it together, and so on. So his whole thesis was exactly what you experienced there. His whole understanding was these uplifts, lakes that drained because of uplift, or lakes that formed because of uplift and then later drained. The draining of Lake Missoula through the Columbia Valley, which was always thought to have been a slow process, is now considered to have been catastrophic, and we have potholes in there that are hundreds of feet diameter and stuff like that. So we've learned a lot more recently about these, and it's from
Well, I'm thinking that, so there's more than one type of earthquake.
Yeah.
It's not the boom and then something cracks.
Well, no, there are actual movements, but the movements are the result of this rebound. So when that rebound gets enough, it cracks it, and then there might be 2 or 3 little movements that go out. And then where it didn't move up there, that's lifting, and that'll go the next time, and so on. They tend to, the Moodus quakes, the Moodus noises, you can read all kinds of stuff about them in the Connecticut literature. They've been investigated in great detail, and they're largely rebound, sounds of rebound quakes. They're out in Rhode Island, they're all over the place in Rhode Island. And you, like I say, you can go right out and see the effects of them on the landscape, where gravel deposits are tilted the wrong way. So it's pretty significant. It amounts to a couple of feet each time you get one. That's a lot. You figure the Atlantic Ocean is spreading a little faster than your fingernail grows. It spreads at about 3 inches a year. Mount McKinley uplifts at about 3 inches a year. The whole Tibetan Plateau uplifts at almost 4 inches a year. Think of the energy to lift the Tibetan Plateau 4 inches a year. And all that energy is available to erode and come out the Ganges. The Ganges River in front of the Himalayas has a riverbed 600 feet thick of gravel because the area has been uplifting and shedding that material up. Phenomenal stuff. And that's because geologic time is so long that you get to look at it, its effects over that tremendously long period of time. All right, anything else? My kids say that's more than I want to know.
I heard on the coast to coast, a weird station, I guess, early in the morning, but that the Mississippi River can split and the ocean would come in. Is that possible?
The Mississippi River has undergone rebound and relocation of its course many, many times.
Oh, really?
And the Youngstown Quake, I mean, there's several of these that have affected it. The Corps of Engineers, the reason the Corps of Engineers does so much work on the Mississippi is really the fact that not only are they harnessing it for use and trying to prevent erosion and so on, they're wrestling with the river, so to speak, but also because the river is prone to catastrophic events, whether they be flood or reroutings. The Yazoo River, southern Mississippi, is the old Mississippi Channel. Just one day it built up a bar, got on the other side of the bar, and never went back. So now you got a river that's abandoned. This happens all the time. If you go down to Terry's Plain Road at Simsbury, the Farmington River has two big meanders that are abandoned there. And they still flood. At 55, they weren't abandoned. They still flood from time to time. In general, they're abandoned morphologically.
Is it really split and have the ocean come?
Well, it isn't a split like you're going to stand there like
Well, I don't mean,
like Lisbon,
no, but I meant kind of separate and
What would happen is there's a great embayment that comes in from Louisiana. And that embayment never used to be land, okay? But it's land now.
Yeah.
And if the up of the Mississippi were to rise and that were to fall, if that hinge were to change from the loading that's going on in the delta in Louisiana, and you turn that, then you would have a swamp that would run up the river. So people talk about that a lot because that would change the drainage patterns so significantly in the country. Look at the in Kentucky. Highest, I don't know if it still is the highest, it used to be the highest suspension bridge was over the Green River. And you have to, I've been on it. You stand there and you look down, and I mean, it's a ways down. And that's a river that used to flow on a flat area. The area slowly kept uplifting, just like the Cumberland region, Kentucky. And that river cut down, and now it's a great meandering river that's in a deep, deep, deep gorge. So you get, it drains all the surrounding area through the limestones. And you have caves that form, and then another generation of caves forms, and another as that river cuts its way down through that. So the Earth's very dynamic, and often we say, well, like you say, can that happen? Yeah, but you and I aren't going to see it,
Can man create an earthquake?
That's a big question now. I think this guy who's promoting this is a nutcase, but he claims that the reason we should stop using fossil fuels is because we're pulling them out of the earth and making earthquakes.
Fracking. Wheeler is putting the fracking, putting the hydraulic fracking into the shales has been causing a lot of microearthquakes.
You get microquakes with that. Absolutely, you have to.
Yes, so there's been a lot of issues with that.
Right. No, locally, that's a very significant process.
Kansas and the South Dakota region.
And we find also, when you mine for coal, you unload the earth, the whole area rebounds. And you stand in a coal mine, stand in any mine, and man, I tell you, it's frightening. You're in there, it's pitch black, it's black like you've never seen dark. It's felty black. And you stand in that moisture, and you hear. All these sounds all around you. And I was in a field trip one time in a large stope, and below a large stope in a mine. You'd have sworn it was a freight train operating there. Noisy all the time. Those rocks just moving that little tiny bit. That grinding noise is amplified. It sounds just like machinery running. It's interesting.
Okay, well, I think we can, one more question?
Feel free to look. Is there another question? Feel free to look at those.
Yeah, we can ask questions
those specimens
later on.
there.
I'd like to thank John for sharing
you're
your
most welcome.
expertise and so token of appreciation, Heartland Land Trust
Now,
decal.
what do I do with this now?
You
Do
can
I
put
put
it
this
on
on
your,
my,
you can
on
put
my
it on
car?
your car, notebook, whatever you'd like. But just, thank you very much.
Thank you.
Yep.